Now, we've briefly, or not so briefly, covered the transactional components of the TIKV cluster. Now, we're going to further expand on the transactional component known as Tidb, or the transactional access to data, or the database known as Tidb. Yeah, let's just go ahead and cover that. So, just a quick recap. This slide was shared earlier, and in this section, we will zoom into the transaction component of this distributed system. So, a quick overview. Tidb is an open source distributed NewSQL database that supports a hybrid transactional and analytical processing, also known as HTAP workloads, which means hybrid transactional analytical processes. It is a MySQL, so this Tidb right here, it's a MySQL compatible and has features such as horizontal scalability, strong consistency, and high availability. Tidb can be deployed on-prem or in cloud. And notice that whenever we receive a transactional operation, Tidb will act as a front end to the TIKV backend data storage layer. Something like this, right? In other words, the Tidb server is a stateless SQL layer that exposes the connection endpoint to the MySQL protocol to the outside world. The Tidb server receives SQL requests, performs SQL parsing and optimization, and ultimately generates a distributed execution plan. And we'll cover it like or we'll just show it the architecture, because this is pretty deep thing. So it's horizontally scalable and provides a unified interface to the outside through load balancing components, such as so we can use different technologies, maybe like a Linux virtual server or an HA proxy or F5. So that would be here at this. Yeah, to the outside world. So yeah, let's say that we have three applications with a MySQL sort of layer. We could load balance to any of these sort of Tidb services. It does not store data, and it's only for computing. So no data storage here. It's only for computing and SQL analyzing, transmitting actual data read requests to TIKV nodes. So yeah, it just performs like the optimization of the SQL dialect per se. But yeah, this is actually a good practice to process data on the actual data nodes, and we'll see why in a second. Okay, so Tidb transactional processing. So let's talk about tables, columns, and rows. Oh my. So in OLTP, which means online transaction processing scenarios, there are many operations such as adding, deleting, changing, and searching for data on a single or multiple rows, which needs the database to read a row of data quickly. Therefore, each key should have a unique ID, either explicit or implicit, to make it quick to locate. So here we're going to talk about just general best practices. So if you've worked with databases in the past, you'll kind of notice a pattern. Many OLAP queries require a full table scan. If you can encode the keys of all rows in a table into a range, the whole table can be efficiently scanned by range queries. So tables. Let's talk about tables. To ensure that data from the same table is kept together for easy searching, Tidb assigns a table ID to each table represented by table ID. Table ID is an integer that is unique throughout the cluster. So usually, data in the same table, we might want to maintain. We might want to keep close by. Columns. Tidb assigns a row ID represented by row ID. Example: column 1, column 2, column 3, etc. to each row of data in the table. The row ID is also an integer, unique within the table. For the row ID, Tidb has made a small optimization. If a table has an integer type primary key, Tidb uses the value of this primary key as its row ID. So basically here we're just saying that the column is sort of represented by an ID. Rows. So Tidb supports both primary and secondary indexes for fast row search. So let's say so we already have the table sort of portion that's ideally locally within the same region, data region. We have that we can quickly scan through horizontally scan through a table by their ID. So if we want to select column 1 and 3, we can just go ahead and quickly scan the row ID. But then how about the row search? So for row search, we're going to have secondary indexes, and this is usually a best practice to prevent full table scans. So both unique and non-unique indexes are supported in Tidb. Similar to table data mapping scheme, Tidb assigns an index ID to each index of the table represented by an index ID. For primary keys and unique indexes, it is needed to locate the corresponding row ID based on the key value pair. So each so for ordinary secondary indexes that do not need to satisfy the uniqueness constraint, a single key might correspond to multiple rows. If needed, to query the corresponding row ID according to range of keys. So the idea here is just to kind of assign an index to each row. So whenever we want to search for a particular, let's say that this can be lexicographically sorted or I don't know. Whenever we successfully find 10 rows by their secondary index, we can just exit the query execution. But generally, it's going to be much more efficient to use this secondary index instead of having to perform a full scan. Yeah, for fast row search. Yeah, okay. Metadata management. So each database and table has metadata that contains various attributes. This information is persisted in TIKV itself. Each database or table is assigned a unique ID, and Tidb uses a dedicated global key value pair to store the latest version of structure information of all tables. Okay, so Tidb's Sql layer. Tidb's Sql layer translates SQL statements into key value operations. It forwards these operations to the data layer, to TIKV. The distributed key value storage layer assembles the results returned by the TIKV. Look back here. And finally, returns the query results to the client, to the caller. The nodes at this layer are stateless. These nodes themselves do not store data right here. They're merely for processing. But this sort of architecture has some obvious problems if we were to talk about a distributed database scenario. So as the data is being scanned, each row is read from TIKV via a key value operation. with at least one RPC overhead, which can be very high if there's a large amount of data to be scanned. It's not applicable to all. If the query is not applicable to all rows, data that does not meet the conditions or criteria does not need to be read. From the returned result of this query, only the number of rows that match the requirement is needed, not the value of those rows. So this is specific to this query. So here in this case, we want to read one row. We want to filter for whatever contains or TIDB in the name, and we just want to return the count, not the actual values. So that's what this means right here. So in this case, we're doing some extra effort or extra computation that's not really needed. So in the next in the next slide, we're going to talk about the distributed SQL layer, not just the SQL layer portion. So to solve the previous problems, the computation should be as close as possible to the storage node to avoid large number of RPC callings. The SQL predicate condition should be pushed down to the storage layer or the storage node for computation, so that only valid rows are returned, which avoids meaningless network transfers between these two components. Then any aggregation function, example, the count function right here, can also be pushed down to the storage nodes and not compute that up here because, yeah, for obvious network reasons, right? That we mentioned earlier, the RPC overhead. So we ideally want to perform all of these operations down at this level and not so much up here. So any aggregation functions must be pushed down to the storage layer for pre-aggregation, and each node only has to return the result of the aggregation and not all the data for further aggregation up here. The SQL layer will aggregate pre-generated results returned by each node. So an example of this is the MapReduce sort of framework that tackles this problem. So let me quickly talk about this. So whenever we want to do a big data processing, let's say that we usually will schedule our workloads to process locally on each node, so that we don't have to be sending data back and forth, causing maybe a network overload right here for each execution stage. We ideally want to, let's say, map the problem to the storage layer, and here we would perform, in this case, it's the filter and aggregation, and then the reduce layer would actually aggregate all of the results from each of the local sort of computation, and just return whatever the final result is per se. This is called the result phase. And this is the result that we'd be sending back to the caller. That's sort of what we just talked about, the MapReduce framework. So we won't get into the details of this architecture, but this is just here for completion. But a single instance of the core SQL layer looks something like this. So there's a set of optimizers, and there's a session also involved here. And so at a high level, the user's SQL request is sent to TIDB server, either directly or via a load balancer. So we talked that here we could load balance. It depends on the use case. It can be like a single client, like this one right here, or it can be a load balanced, different a pool of so different processes per se. In Kubernetes, you would call this different pods enabled with the MySQL sort of client. So we would load balance either directly talk to the TIDB server or via a load balancer. TIDB server will parse the MySQL protocol packet, get the content of the request, parse the SQL request syntactically and semantically, develop and optimize query plans. Where's the query plan? Execute a query plan and get the and process the data. All data is stored in the TIKV cluster, so it's so in this process, TIDB server needs to interact with TIKV and get the data. Finally, TIDB server needs to return the query results to the user, just as we spoke over here. Yeah, it's all a dance between like the query plan that you need to execute and how it's going to get mapped to the data layer. Okay. So next we're going to show a demo of how we would interact with a MySQL application for transactional processing or querying or operations.